we're going to talk about applications and models of exponential growth and decay in section 4.6. The exponential growth or decay model, it's going to grow if the function is increasing, and if the function is decreasing, we call that exponential decay. So it is a function in terms of time. The book just writes y. I prefer to be more specific and say f of t. So this is a function in terms of time. Because we have a few different symbols here, we know that since it's f of t, the independent variable is t. So time, which can be given in various units of time, depending on the situation, is the independent variable, and f of t is an amount. So time would be greater than or equal to 0. So the exponential function without application has a domain of all real numbers, but in exponential growth or decay, we're specifically saying that t is time. Time is non-negative, so the domain, we need to make a note that the domain is 0 to infinity. Now the amount, we're talking about a physical amount, and if you just look at an exponential growth curve, you know that amount is going to be positive because the exponential function is asymptotic at y equals 0 anyway, so the range is still the same as it would be. It could potentially be like if we were to shift it or something. So f of 0 is the initial amount, and k in the exponent of the base e, that's a constant, and if k is greater than 0, that's going to make the function increasing, and if k is less than 0, function is going to be strictly decreasing. So given f of t1 equals a1, so a specific time equals a certain amount, we're going to solve for k. So a lot of times in these, you end up needing to determine the exponential model before you can go and answer any questions. So we need to figure out what this constant k is. Now t1 is a specific time, so I'm going to do this with the generic values, and then we'll do this in an example with specific numbers. So I'm going to divide by the initial amount, so I have a certain amount, which I'm calling a1, which is paired with the independent variable t1. Divide by that. Now the variable that we're solving for is in the exponent, and the base is e, so we want to take the natural log of both sides. And the natural log of e to the kt1 is just k times t1. So the power property of logarithms, the exponent would come out front. The natural log of e is 1. So we would have the natural log of a1 over a0 equals k times t1. Now t1 is just a number, so we would divide by that number to isolate k. And k is always going to be equal to the natural log of the amount at time 1, whatever time you're given, divided by the initial amount, and then that number is divided by the time you are given. So if you want to use this and think of this as a formula for k, that's totally fine. It'll work every single time. You may not need to reinvent the wheel if you just skip straight to here. Otherwise you would need to solve this equation every time. So what I want to bring to your attention is that continuously compounded interest is just a specific application of exponential growth. So a equals pe to the rt, that constant k in our exponential growth model is the same as specifically in finance where R stands for, the interest rate. T is still the independent variable, and f of t is the dependent variable. So the amount A, which is the future value in the continuously compounded interest, is the function value, f of t, and then of course E is E, and here we've got initial amount, and here we use P. P is the initial amount. In finance we would call that the principal. So I just want you guys to realize that those actually are the same thing. So if you can mesh those concepts together, realize they're the same thing, you have a better chance of learning both of those. So let's look at the first example. How long will it take for an investment to double if continuously compounded at 8%? So if we want to double our investment, that means the amount needs to be twice the original amount, which we call the principal. So A equals 2P. If you're asking about something doubling or tripling or quadrupling, you're going to end up at this next step every time. So these are some very common, questions. So you can, go straight to what I'm about to show you, but we're going to answer specifically 8%, but we're going to take the natural log of both sides, and that's going to equal RT. So the natural log of 2 divided by R equals T. This, and I'm going to plug in the rate on the next line. So if the question says how long did double if continuously compounded, the time always ends up being the natural log of 2 divided by the rate. So there's this nifty little trick that finance professionals like to use, called the rule of 72. And it really should actually be the rule of 69, or maybe the rule of 70, but the rule of 72 simply states this, that if you take 72 divided by the interest rate as a percentage, that's approximately the time to double. The natural log of 2 is actually approximately 0.69. So when you divide that here, so 0.69 divided by 0.08, that's our time. The little trick for the rule of 72, and I'm getting about 8.6 years. For whatever reason, in finance, they say take 72, divide it by the rate as a percentage, and you're going to get approximately the time that it takes to double. So if we did 72 divided by 8 per this rule of 72, that's 9. So the rule of 72 gets you close, but again, it's always going to end up being this natural log of 2 divided by rate. So but the natural log of 2 is closer to 0.69 than 72, so you would be better off doing 69 divided by 8%. So 69 divided by 8% is going to get you closer. I'm not a financier. I'm not sure why they went with 72 on this, but now it's always going to end up being the natural log of 2 divided by your rate as a decimal will give you the time to double. So if it said triple, you would want to change that 2 to a 3. So the time to triple your investment continuously compounded, that type of thing. What comes to mind, and again, I'm not, I'm a statistician, not a, financial advisor. What comes to mind is the natural log of 2 is 0.69. That's continuously compounded. They might be using 72 for something that is closer to an annual rate of return. So my guess is that's why it ends up being the rule. But regardless, it's good to know. A quick approximation. Take 72 divided by your rate as a percentage, and that gives you, approximately your time. So it's just a shortcut. But here's the math that we want to be able to do. Okay, let's take a look at exponential growth of a population. A population initially has 20 million. We could say a particular region or a country, it doesn't matter. 30 years later, the population is 32 million. So populations grow exponentially, which the idea behind exponential growth is that the outputs of the function continue creating more outputs, and nothing describes that more easily than a population. The amount of, in this case, humans in the population is what is going to compound and create more humans. Humans create more humans as time goes on. So, under the controlled circumstance of just, let's say we got a country of 20 million and, we don't have anything crazy going on that we want to examine. We're just looking at the math here. We take an observation, 30 years later that the population has increased by 12 million. We are going to use an exponential growth model for this rather than like a y equals mx plus b or something. So part A, we're going to give the growth model. And we're going to need to solve for k. So f of t equals a naught e to the kt. And our initial amount is 20. Now on the previous page I said if you have a specific time and a specific output amount, we were calling that T1 and A1. So in this situation we have an output of 32 when the time is 30. So if we look back at the previous page, we're solving for k right here. T1 and A1 are specific amounts, so here in this example we have those amounts. So there's A0, there's A1, there's T1. So we can just, we don't have to reinvent the wheel. We can just use what we've already solved here. The natural log of 32 over 20 divided by 30 is the exact value for k. And let me type that into the calculator real quick. I didn't have that pulled up. And we're going to approximate to something that's reasonable, based on the situation. And something that looks reasonable here is 0.00. I'm going to say it's 215, so I'm going to round that to 0.0022. If you have the online homework, just follow their rounding instructions. 0.0022 is a logical approximation for what I'm doing here. So the function we know to be f of t equals 20 e to the 0.0022 t. Now it says, what will the population be when t equals 40? So that means f of 40 equals 20 e to the 0.0022 times 40. And let me get that answer real quick. And that is approximately let me check that value real might be off on a decimal here. I think that's 0.02. Let me check that. Oh, I typed in the calculator wrong. I'm right here. So we have, this is all correct. I just typed in the calculator wrong. I'm sorry. 0.016. I need to change that. 0.016. Okay, so now I'm going to type 0.16 this into the calculator. So let's just do this all together. Hopefully you've got your calculator and you're doing this also. And I'm getting 0.64 when I 0.016 times 40, so that's 0.64. And that's about 1.896. Okay, so we approximated along the way. We approximated, this is an approximation, which then makes this an approximation, and then this is an approximation. So depending on how you round and where you approximated, this number is going to be a little different. I should actually use the approximately equals here. We'll just put them, they're all approximations, so they're all approximately equal to each other, and we're going to be pretty close to 37.9 million. So 37.9 million population when t equals 40, and then part C, it says how long until the population is 60 million, so we want to set our output to 60, so the units are already in millions. 60 equals 20 e to the 0.016 t, and this is going to be the same question as saying how long until the population triples. So if you went back and looked at the previous example, so the natural log of 2 over the rate for doubling your investment, so this ends up being the exact same scenario. We're going to triple the amount, and then rather than using an r, we have we call it k and just the generic exponential growth. So the natural log of 3 divided by 0.016 is the time to triple. So if you were going to show every step, you would divide by 20, take the natural log of both sides, and then divide by 0.016. However, we know that if it's double, triple, quadruple, whatever, since it says triple, the formula is always going to end up being the same. Natural log of 3 divided by whatever the constant is. If it's compound interest, we specifically call that rate. In this case, we call it just a constant k. So let's get an approximation there. And it looks about like 68.7 years. 68.7 years until 60 million. Part of that population is 60 million. Okay, so then an example of exponential decay is radioactive substances, and we just call it radioactive decay. So the half-life, and here's more of a mathematical statement maybe than this is how we need to understand it. If we input the half-life t1, so we're going to say some time is known to be the half-life, the output is the initial amount divided by 2. So, and this is an exponential decay model, so that doesn't mean and t1 plus t1 is the input, then there are 0, that would be linear. It means every every amount for the half-life, every amount of time for the half-life, the amount is halved. So an example would be the half-life of a certain radioactive substance is 235 years if 50 grams is present initially. So what this tells us right here is that F of 235 equals 50 divided by 2. And that's mathematically, that's what half-life tells us. So we need to give the exponential decay model. We need to determine how long until 12.5 grams is present, and then how long until 8 grams is present. So let's take a look at the exponential decay model. It always ends up being the constant k always ends up being the natural log of 1/2 divided by the time that is given for the half-life. So the natural log of 1/2, in this case the half-life is 235. The reason for this is very similar to the previous question when we said we want to double or we want to triple. We want half of the amount. So every time you solve, and let's just do that real quick. Every time you solve this, you will end up with k equals the natural log of 1/2 divided by the half-life time. So if we know that we have 50 as the, let's see, how much is 50 grams is initially present, so half of that is 25, e to the k, and then the time for the half-life is 235. So we would take 25 over 50 equals e to the k times 235, which is 1/2, equals e to the, I like to write 235k rather than k times 235, to natural log and e to the x are inverses, so we're going to take the natural log of both sides. And power rule would mean that the exponent comes out front. Natural log of e is 1, so the natural log of 1/2 equals 235k. Divide by 235, divide by 235. And the natural log of 1/2 is negative 0.69, and then you divide that by 235, you're going to get a negative number, which is approximately 0.003. I'm going to round it there. And we know that we're going to get a negative number here because the function needs to decrease. So k is going to be negative for an exponential decay function. So f of t equals 50 e to the negative 0.003 t is the answer to part A. Now part B we can do analytically, but let's plug in the amount 12.5, solve it, and then we'll show you what I mean by when I say we can answer this question analytically. So how long until 12.5 grams is present? And so when we do the natural log of 1/4 and divide that by negative 0.003, so since this is an approximation, well, I'm getting approximately 462 years, but the answer is exactly 235 times 2, which is 470. So the reason for this is the exact value. This is an approximation because I rounded right here. Every 235 years, half of the amount is gone. So if we start with 50, excuse me. So if we start with 50, then when t equals 235, a equals 25. So we're cutting the amount in half. Then if we go another 235 years, we get half of that amount. So a equals half of 25 when t equals 470. This isn't a number line, I'm just giving you a visual of here's the entire amount, cut it in half at, well, I'm going to say the first half-life, so 235 years, then cut that in half at the second half-life. Now, then you would cut it in half again, so when t is 705, so another 235 years, the amount is 6.25. So every 235 years, you have half as much as you did in the previous half-life. So we keep having the amount every 235 years. So that answers part B. So if you were doing the math and you had this right here as an approximation, then you would, my calculator showed me 462 as an approximation. However, from the start, we could have said, well, 235 years, the amount is 25, so 470 years, the amount is going to be 12.5, and that was the purpose of that amount specifically. Part C, 8 is not a power of 1/2, with the original amount being 50, so we have to solve like we would normally. So we set 8 equal to 50 e to the negative 0.003 t. So we're answering the question, how long until 8 grams are present? So we want the output of 8. Here's the initial amount. We know the exponential constant is approximately negative 0.003, but we don't know the time. So 8 over 50 equals e to the negative 0.003 t, natural log both sides. 8 over 50 reduces, we'll reduce that in just a second. And then divide by the constant there, which is now the coefficient. And type that into the calculator. Getting about 611 years, which is a logical answer. We know that it needs to be greater than 470 years because at 470 years it's going to be the second half-life, so we'd only have 12.5 grams present. Okay, there's some applications of exponential growth and decay.